Imagine trying to understand something that can, clog up massive pipelines. But at the same time, it's so small you need like super advanced simulations just to see how it sticks together.
Yeah, it's kind of the paradox of oil and gas exploration, isn't it? That huge range of scale.
Exactly. And that's pretty much what we're diving into today,
Yeah.
unpacking these complex situations.
What really gets me is how it pulls from so many different scientific areas. You've got molecular interactions on one end and then massive geological forces on the other. It's a real crossroads.
Absolutely. And for this deep dive, it's really your curiosity, listener, that's guiding us. We're digging into the latest research, the stuff pushing the envelope on how we find and extract oil and gas.
Mm-hmm. We've gone through a stack of academic papers, research focusing on, the nitty-gritty processes, the chemistry, the geomechanics.
And our mission, really, is to pull out the most important insights from all that complex material, to give you a clearer picture of the challenges, but also the innovations happening right now.
Making it digestible, yeah.
Yeah.
Without losing the core ideas.
Okay, so this field is huge. Where do we start? Well, one challenge that keeps coming up in petroleum processing is these tiny things called asphaltenes.
Asphaltenes, yeah. Think of them as the heavy, really sticky bits in crude oil. The main issue is they like to clump together, aggregation, we call it.
Right.
And then they precipitate, basically drop out of the oil. That causes blockages, messes with efficiency, pipelines, refineries, the whole lot.
Exactly. And, despite tons of experiments, how exactly they clump together, well, it's still debated.
It is, which is why, alongside the lab work, there's this huge push on the theoretical side, using computers.
Right, the computational stuff, trying to predict how these molecules actually behave, like atom by atom.
Precisely. Trying to nail down the fundamental forces. Some models use colloidal theory, treating asphaltenes and similar molecules, resins, as sort of pseudoparticles.
Okay.
Then you have more complex things, equations of state, PREOS, CPAEOS, you might hear those acronyms. They're mathematical descriptions of how pressure, volume, temperature all relate for these complex mixtures.
And they often bring in something called Wertheim thermodynamic perturbation theory. Sounds heavy.
It does, but it's essentially a way to account for how sticky or associative these asphaltene molecules are, their tendency to, associate.
Gotcha. So what are the big takeaways from all these computer simulations? What have we learned?
A really consistent finding is how the flat parts of the asphaltene molecules, the polyaromatic cores, like to stack up, like pancakes.
Okay.
This parallel stacking seems to be a major driver for aggregation in different liquids, different solvents like toluene, heptane.
Stacking. Okay. But you mentioned heptane specifically.
Yeah, interestingly, in heptane, the simulations also showed these molecules arranging in kind of T-shapes within the clusters, not just stacked pancakes.
Wait, T-shapes. That's
Yeah.
unexpected. What does that suggest?
It really underlines how the liquid environment, the solvent, isn't just passive. It actively influences how these molecules get together and arrange themselves.
Right.
And speaking of solvents, they've looked at how they affect aggregate stability at high temperatures, too. Like a molecule called quinolone seems to disrupt the stacking, makes the clumps less stable. Whereas another similar one, 1-methylnaphthalene, didn't have nearly as much effect. So the specific solvent chemistry really matters.
It's like the solvent molecules are either pushing them together or pulling them apart.
That's a good way to put it. Some studies calculate something called the potential of mean force, the PMF. Think of it like mapping the energy as two asphaltene molecules get closer.
Okay, like an energy landscape.
Exactly. And using that with a technique called umbrella sampling, they can figure out the energy needed for two of them to pair up, form a dimer. Now here's a twist. Some studies found similar energy needed in both toluene and heptane.
Wait, but you said they behave differently in those solvents.
Right. It seems contradictory. But other work suggests maybe the toluene molecules themselves interact with the asphaltenes through what's called para interactions, the attraction between those flat aromatic rings.
Oh.
And this interaction actually makes it easier for the asphaltenes to associate in toluene compared to heptane. So it reinforces this idea that pop interactions are crucial, and their strength depends on the structure, the number of rings, other atoms involved.
So these tiny flat bits want to stack, and the fluid around them can either help or hinder that stacking, like puzzle pieces.
Good analogy. Yeah. But these super detailed simulations, molecular mechanics, molecular dynamics, they take huge amounts of computer power.
Right, so you can only look at small bits for short times.
Exactly, which is where mesoscopic simulations come in. They're like Using bigger building blocks to represent groups of atoms lets you simulate larger systems for longer.
Or coarse-grained.
Right. And with things like GPUs speeding things up, they're getting results like diffusion rates in toluene that actually match experiments. That's a big deal for validation.
So progress is being made on the modeling front. But what's the bottom line for dealing with asphaltenes practically?
The key insight is that this aggregation is driven by stacking, and that stacking is influenced by the solvent. So theoretically, if you can tweak the solvent environment, maybe with additives,
You could control the problem.
potentially, yes, prevent or manage the precipitation. The big challenge, though, is getting models that work reliably for all the different types of crude oil and conditions out there. Many current models are very specific to the data they were built on.
Okay, so asphaltene's a persistent molecular puzzle heavily influenced by the surrounding liquid. Let's shift gears now to something, well, not even more visible, but still super complex. Gas hydrates. I still find it wild that natural gas and water can freeze together like that.
Gas hydrates, yeah, they're fascinating. And they're kind of a double-edged sword.
How so?
Well, on one hand, they're a huge nuisance for the industry. They can block pipelines, cause major flow assurance problems.
Right.
But on the other hand, they represent potentially colossal reserves of natural gas trapped in these ice-like structures under the seabed in permafrost.
A potential energy source.
A massive one. Plus, there's an environmental angle. If these hydrates become unstable and release methane, which is a potent greenhouse gas that could have serious climate implications.
So how are we trying to understand these things better, these icy gas cages?
Numerical simulations are absolutely crucial. They help us understand how hydrates break down, dissociate, and predict how reservoirs containing them might behave if we try to produce the gas.
So modeling how to get the gas out safely and efficiently.
That's the main goal, yeah. The basic idea is to change the conditions in the reservoir, the pressure or the temperature, to make the hydrates unstable, force them to release the gas.
Sounds simple enough.
But the actual process down in the rock is incredibly complex. You've got heat moving around, fluids, gas, and water flowing, and the chemical reaction, the kinetics of the hydrate breaking down itself, all happening at once.
A real interplay of physics and chemistry.
Exactly. And the tricky part is these processes are all coupled. They affect each other. As the hydrate dissociates, the rock's permeability changes, which affects fluid flow. The thermal conductivity changes too, affecting heat transfer.
And you mentioned something else, the rock itself.
Right. Many early models just assumed the rock structure stayed put, rigid. But we now realize that in some formations, the hydrates kind of act like cement. They add stiffness.
So when they break down, the ground can actually get weaker.
Potentially, yes, which adds a whole geomechanical aspect. So now simulation models get classified based on what they include. You have HC, hydrochemical,
Flowing chemistry,
TC, thermochemical,
Keaton chemistry,
THC, thermohydrochemical,
I have 3.
and then the big one, THMC, hydrothermomechanochemical, which adds in the rock deformation, the geomechanics.
Wow.
And as computers get more powerful, the trend is definitely towards these more complex THMC-type models, trying to capture everything.
It's like building a virtual reservoir in the computer.
Pretty much. And within these models, you need to define how things like heat conductivity work. Often it's a weighted average of all the components: rock, water, gas, hydrate. You need models for relative permeability, how easily gas versus water flows, depending on how much of each is present.
Like the Van Ganukten or Brooks and Corey model.
Exactly, those types of relationships. And then you need a model for how fast the hydrate actually breaks down the kinetics. The Kim-Bishnoi model is a common one there, often relating the rate to how far you are from equilibrium conditions.
And the fluid flow part, still Darcy's law.
Mostly, yes. Darcy's law is the bedrock for flow in porous media. It gets extended for multiphase flow using those relative permeability concepts we just mentioned. And like we said, the more advanced models are now trying to incorporate geomechanics, pore pressure changes, stress evolution in the sediment.
Okay, building these models sounds incredibly complex. How do you even know if they're right?
Yeah.
If they predict reality?
Validation is key, absolutely critical. Researchers compare simulation results against lab experiments and against the limited field data we have from actual hydrate production tests.
Field data must be hard to come by.
It is relatively scarce. But there's also mutual validation, different modeling groups comparing their results. As more pilot projects happen, we should get more real-world data to test against.
So what are these models actually used for? What questions can they answer?
A whole range. estimating production potential. How much gas could we realistically get? Analyzing wellbore stability, making sure the hull doesn't collapse during production.
Right.
Looking at CO2 injection, could we store CO2 in hydrates and maybe get methane out at the same time? Understanding how hydrate layers affect conventional gas reservoirs underneath them.
And comparing production methods, like depressurization versus heating.
Exactly, evaluating the effectiveness of different techniques. Depressurization, just lowering the pressure, is generally seen as the most promising economically. Thermal stimulation injecting heat can work, but it's often energy intensive.
What about injecting chemicals?
Yeah.
Like methanol?
Methanol is used to prevent hydrate formation in pipelines, but using it to break down large amounts in a reservoir. Probably not very effective. The low permeability of hydrate zones limits how far the chemical could reach. Any effect would likely be very close to the well.
Okay.
What the simulations consistently show is that the dissociation rate is super sensitive to temperature and pressure. Get those wrong and nothing happens, or it happens too slowly.
And there are potential downsides.
Yes, they also predict that you can get really high pressures building up right at the dissociation front. That could cause problems fracturing the rock or causing it to compact. Geomechanical issues.
It sounds like doing this in the field is way harder than in the lab.
Oh, absolutely. Scale is a huge factor. In the lab, the intrinsic chemical rate might dominate. In the field, it's often about how fast you can get heat to the hydrate and get the gas and water away.
Heat transfer and fluid flow become bottlenecks.
Right. In permeable rocks, the movement of hot fluids might be more important than just heat conduction through the rock. And there's still this ongoing debate. Are equilibrium models good enough, or do you really need to model the kinetics, the actual rate of dissociation?
Okay, from icy hydrates, let's switch to something that's really transformed energy production recently. Hydraulic fracturing. Fracking.
Yeah, hydraulic fracturing has been absolutely pivotal for unconventional resources. Shale oil, shale gas, unlocking formations with incredibly low natural permeability.
The basic idea being pumping fluid down at high pressure to crack the rock.
Essentially, yes. Create pathways for the oil and gas to flow. And a key technique is using horizontal wells with multiple fractures created along their length.
Multi-stage fracturing.
Yeah.
And how do engineers analyze how well that works?
Well, a lot of their early analysis made a simplifying assumption that the fractures are infinitely conductive, meaning no pressure drop along the fracture itself.
Not totally realistic, but makes the math easier.
Exactly. It's a starting point. Then people developed methods to approximate solutions for finite conductivity fractures. They also looked at things like the response to a sudden pressure drop at the fracture face, what they call a unit step pressure decline.
That sounds pretty theoretical. How does that help with real wells?
It's like a fundamental response function. If you know how the reservoir reacts to that simple pressure change, you can use a mathematical tool called Green's functions to figure out the pressure behavior when you're producing at a constant rate, which is more realistic.
Okay, building complexity from simpler cases.
Right. And interestingly, even that simple infinite conductivity assumption often gives surprisingly decent estimates for the total amount of oil or gas you'll eventually recover. Maybe not perfect for the fractures right at the ends, but pretty good overall for cumulative production over time.
So simplified models can still be quite useful for the big picture, the ultimate recovery.
They definitely can be. Now, stepping back a bit, the way fluids interact with the rock surface, the interfaces that's crucial in many areas, not just fracturing.
You know, things like wettability, how much the oil or water likes the rock surface.
Yeah.
And how they mix or stick.
Exactly. Wettability, diffusion, absorption. These interfacial processes are fundamental to things like enhanced oil recovery or EOR.
Getting more oil out after initial production slows down.
Right. Often that involves injecting fluids, water, gas, chemicals to push more oil out. Chemical injection, for instance, often aims to lower the interfacial tension between the oil and the injected fluid. Makes it easier to mobilize the oil trapped in the tiny pores.
Like adding soap to greasy water.
Kind of, yeah. Reducing that resistance at the interface. And molecular simulations are giving us amazing insights here.
Seeing how molecules behave right at that oil-water-rock boundary.
Yes. How crude oil components orient themselves, how CO2 interacts. Simulations show how molecule length affects alignment at interfaces, and they help explain why supercritical CO2 works so well for EOR. It mixes better with oil, lowers that interfacial tension.
Seeing the mechanism at the molecular level. What about other applications of understanding interfaces?
Well, nanoparticles are a hot area. Using them to potentially alter wettability for EOR, or even designing membranes for CO2 separation?
Like filters for gases.
Exactly. And simulations are vital for understanding methane hydrate formation at the nanoscale, too, watching how those first crystals start to form, which is really hard to see experimentally.
And for preventing hydrates.
Yes, designing better kinetic hydrate inhibitors, KHIs, molecules that slow down hydrate growth. Computational screening helps identify promising candidates much faster than just lab testing everything.
So computers help design solutions too. What about carbon capture? That involves interfaces, right?
Hugely important there. Carbon capture and separation, CCS. Designing materials adsorbents that selectively grab CO2 out of flue gases or natural gas. That all comes down to how CO2 molecules interact with the material's surface.
Absorption.
Right. And computational methods like DFT, density functional theory, or Monte Carlo simulations let us predict how strongly CO2 will bind to different materials. Helps us design materials with high CO2 selectivity.
It really is all connected, tiny molecular forces tackling huge global challenges.
Okay, let's zoom out again to the solid rock itself. Petroleum geomechanics. That's about how the Earth's stresses affect reservoirs, right?
Exactly. How the rocks deform, how stresses change when we drill or produce fluids. And ignoring it can have big consequences. The classic example is the Ekofisk field in the North Sea.
What happened there?
Significant reservoir compaction, the reservoir rocks squashed as oil and gas were produced, led to the whole seabed sinking. And the platforms on top of it, it was much more subsidence than initially anticipated.
Oh, a costly oversight.
Definitely. It really drove home the need for good geomechanical prediction and management.
So how do we predict and prevent that sort of thing now?
Computational modeling is standard practice. Using methods like the finite element method, FEM, or the displacement discontinuity method, DDM, to simulate how reservoirs compact and how that translates to surface subsidence.
And for wellbore stability, preventing collapses during drilling. Predictive models are crucial there too. They usually involve solving coupled equations, poroelasticity equations. These link rock deformation, pore fluid pressure, maybe solute concentrations, and temperature. They're all interconnected.
It sounds complex to solve.
It is. FEM is commonly used. But modeling how things move with the fluid flow advection can be numerically tricky, so special stabilization techniques are often needed. People run simulations of well bores under different stress conditions, considering thermal effects, chemical effects, and how the rock might deform permanently elastoplastic behavior.
And what about simulating fractures starting and growing?
For that, there's the extended finite element method, XFEM. It's clever because it lets you model cracks growing without having to constantly redraw the whole simulation grid, which saves a lot of effort. And models are getting better at coupling fluid flow in both the rock matrix and the fractures with the overall mechanical deformation.
Building ever more realistic virtual rocks. Now, shale is a special case, right? You mentioned anisotropy earlier.
Yes, shale is very anisotropic. Its properties, stiffness, strength, even permeability and electrical resistivity depend on direction, usually related to the layering, the bedding planes.
And shale resources are huge, especially in the U.S.
Enormous. Plays like the Bakken, Eagle Ford, Marcellus, huge amounts of technically recoverable oil and gas.
So how does that anisotropy affect drilling in shale?
It's critical for wellbore stability analysis. You need to calculate the stress concentration around the wellbore, considering the natural stresses and the mud pressure, and how they interact with the rock's directional properties. Failure criteria, like more Coulomb, have to be adapted to account for the weakness along those bedding planes.
With those layers we see in shale outcrops.
Exactly. Shale is often modeled as transversely isotropic, or TI. Think of it like wood grain, strong along the grain, weaker across it. Mathematically, you use compliance or stiffness tensors to describe this. And researchers are finding clever ways to use measurements, like how sound waves travel through the shale acousto-elastic parameters to estimate things like the maximum horizontal stress, which is really important for predicting fractures. Clay content also plays a big role in the anisotropy.
And the well direction matters.
Absolutely. Drilling direction relative to the bedding and stresses significantly impacts stability. The cohesion and friction of those bedding planes are key inputs for anisotropic models. Studies on formations like the Bakken have helped map out stress conditions and identify zones with potential overpressure.
So understanding that directionality is vital for successful shale wells. Let's zoom right in now, down to the nano level within the shale itself. How do we characterize that?
Getting good measurements at the nano and microscale requires meticulous sample prep, grinding, polishing, then often using things like ion milling or focused ion beam, FIB, milling to get pristine surfaces.
Okay, super smooth surfaces. Then what?
Nano indentation is a key technique. You press a tiny sharp tip into the surface, measure the force and depth very precisely.
Like poking it with a tiny needle.
A very, very precisely controlled needle, yeah. Analyzing the curve of load versus depth, often using the Oliver and Farr method, gives you stiffness, Young's modulus, and hardness at that tiny spot.
But shale's mixed up, right? Different minerals, organic bits.
Highly heterogeneous, yes. So you do lots of indentations and use statistical analysis to get a picture of the different components. Studies on Barnett, Marcellus, other shales clearly show the organic matter. The kerogen has very different mechanical properties from the minerals around it.
So you can map out the properties. What else?
Microcantilever beam tests, making tiny beams of shale and bending them till they break, gives strength info. You can combine that with EDS analysis to know the exact mineral mix at the test spot.
Wow.
Then, at slightly larger scales, you have scratch tests, fracture toughness tests. They show the anisotropic response too. And Brazilian tests squeezing disks of shale measure tensile strength and how it changes with bedding orientation and mineral content, like clay versus carbonate.
So a whole suite of tools to probe shale mechanics from nano to micro to macro. How do we link all that up? Connect the nanoscale stuff to how a whole reservoir behaves.
That's the challenge, integration across scales. Combining experiments with multi-scale modeling. At the large scale, you have continuum models, elasticity, plasticity, damage mechanics, or discrete models, DEM, lattice models, which treat the rock as particles or elements.
Discrete models are better for fractures.
Often, yes, because they can explicitly model breaking bonds or interfaces. You can model fractures as smeared zones of weakness or as distinct surfaces. There are also specific constitutive models for anisotropic damage in shale. And hybrid FEMDEM models are powerful for complex fracturing.
And you mentioned another one, LDPM.
Lattice discrete particle model. It's a mesoscale approach, kind of bridging the gap. It incorporates heterogeneity and models fracture by breaking links in a particle lattice. It can capture the layered shale structure and anisotropic strength quite well.
So building virtual shales from the ground up, connecting tiny properties to large-scale behavior.
Okay, thinking about hydraulic fracturing again. Once you've made the cracks, how do you get the gas out effectively, especially from those tiny shale pores?
Great question. The hydraulic fractures are the highways, but most of the gas is stored in the side streets, the nanopores in the shale matrix. Long-term production relies on gas diffusing from those tiny pores into the bigger fractures.
A diffusion process.
Right. Models have been developed to analyze this, estimating the fracture network's volume and surface area. You can look at the relationship between fracture spacing and gas flow rate.
To figure out an optimal spacing.
Exactly. Or work backwards from the production decline curve over time. That decline tells you something about the effective spacing and connectivity of the fracture network you actually created.
Clever. Using the production data itself to diagnose the fracture system. What about how those fractures interact? Can they mess each other up? They can. You can get localization instabilities. If the fluid pressure isn't uniform, especially near the tips, some fractures might grow much more than others, or even stop. Kind of like in some geothermal projects.
So you don't get a nice, even network.
Right. You get channeling, which is less effective for draining the reservoir. You need a fairly uniform pressure profile to keep multiple parallel cracks growing efficiently. Models like the crack band model help simulate this localization within finite elements. It all comes back to understanding that coupling between fluid flow and rock deformation.
A delicate balance to get right. Hey, let's shift perspective slightly. Talk about the materials themselves, especially when they're not fully saturated with water. Soils, sediments.
Right. The hydromechanical behavior of unsaturated granular materials. Crucial because you often encounter partially saturated zones. The key concept here is matrix suction. Yeah, it's the negative pressure of the pore water relative to the pore air pressure. Comes from capillary forces in the tiny pore spaces. Think of capillary rise, how water climbs up a narrow tube. Same principle holds water in soil pores against gravity.
And smaller pores mean stronger suction.
Exactly. The relationship between water content and suction is the soil water retention curve, SWRC. It depends on the soil's void ratio, pore structure. Models like Van Genuchten or Brooks and Corey describe this curve, often using pore size data from mercury intrusion porosimetry, MIP.
Okay. And stress is different too.
Effective stress becomes more complicated in unsaturated soils. There's still debate on the best way to define it for modeling. Suction also affects the soil's stiffness, its volume change behavior when wetted or dried.
So drying soil can shrink it, wetting can swell it.
Yes, and that needs to be accounted for. Lab tests like odometer and shear tests help relate strength and deformation to effective stress and suction, often using modified Moore-Coulomb criteria. It adds another layer of complexity compared to fully saturated conditions.
Definitely more going on when air is in the pores. Okay, broadening out again. Beyond oil and gas, can we use similar knowledge for other energy sources? Geothermal.
Absolutely. Enhanced Geothermal Systems, EGS. Harnessing Earth's heat where you don't have natural hot springs. The idea is to make an artificial reservoir in hot, dry rock.
Inject water, fracture the rock, circulate water to heat it up.
That's the core concept. And interestingly, sedimentary basins where we find oil and gas are also potential EGS targets, so-called sedimentary EGS or AEG.
Using oil and gas tech for clean energy.
There's a lot of overlap in the subsurface understanding and techniques needed. Conceptual models for EGS look at how the injected cold water front moves through the hot rock, extracting heat. Permeability, especially fractures, is key.
Simulations help predict performance.
Essential. Modeling fluid flow, heat transfer in the porous rock and fractures. They show how, say, one big fracture can really channel the flow and affect the heat extraction.
Is geothermal growing much?
It's still relatively small in the U.S. energy mix, but there are big pushes to expand it. Projects like Forge are focused on advancing EGS technology. We also need to understand how injecting cold water changes the stresses around the reservoir thermal stress effects. Distinct thermal zones develop.
Fascinating overlap. Okay, finally, let's touch on the factor underpinning all of this. The economics?
Can't ignore the economics in oil and gas exploration, for sure. Economic models look at estimated recoverable amounts, the chance of drilling a dry hole, oil and gas prices, exploration costs, all of it.
And exploration definitely follows prices, right?
Strongly. High prices mean more exploration activity. The historical data is very clear on that. It justifies the risk.
What other big economic trends?
A major one, especially in places like the Gulf of Mexico, is the move to deeper water over the last few decades. Shallow water production has declined. Deep water has grown.
Which means different technology, higher costs.
Exactly. Affects rig types, contract lengths. Deepwater rigs are complex, expensive, contracted for longer periods. Statistical analysis confirms water depth and oil prices heavily influence drilling contracts.
Are we getting better at finding oil and gas? Fewer dry holes?
The data suggests, yes, the probability of dry holes has generally decreased over time. Better seismic imaging, better geological understanding. It makes exploration more efficient, reduces risk, especially when targeting known productive areas.
So technology improves the economics too.
Absolutely. It's a constant feedback loop between technology, geology, and economics shaping the industry.
Wow. Well, we have certainly covered a massive amount of ground, from molecules sticking together right up to global economics and deep water rigs. It's really clear this is a field that's constantly pushing scientific and engineering limits.
It really is. And what strikes me is how interconnected it all is. Nanoscale properties influencing massive engineering projects and their economic viability. It's quite something.
And hopefully, for you listening, we've managed to connect some dots, give you those aha moments without drowning you in the jargon. That was the goal.
Yeah, navigating the complexity.
So thinking ahead, here's something to ponder. As technology keeps advancing, as our energy needs evolve, and as the pressure to, minimize environmental impact grows, how will all that continue to shape these frontiers of finding and extracting energy? Where does that balance lead us?
That's the multi-trillion-dollar question, isn't it? Balancing energy security, economic reality, and environmental stewardship.
Yeah.
A constantly shifting equation.
Indeed. Well, thanks for joining us on this deep dive. If anything specific caught your ear, we definitely encourage you to explore it further. Until next time.